It's the coldest, driest, highest, and windiest continent on Earth. Despite its reputation for the fiercest weather on the planet, Antarctica is a hotspot for scientific ballooning. The reason is Antarctica's circumpolar winds.
Cool.
Yeah.
That was awesome.
That was awesome.
These high stratospheric level winds set up during the Antarctic summer and circulate around the South Pole in a counterclockwise direction. This means NASA's giant scientific balloons, the largest being nearly 40 million cubic feet, can be launched, ascend to 120,000 plus feet, the edge of space, and sail the circumpolar wind around the continent for 10 to 20 days on average. And in some of the most successful instances, flights can be terminated, and the balloon and payload recovered, all within 100 miles of where they were launched. Riding this Antarctic vortex in 2008, a 7 million cubic foot super pressure test balloon flew for 54 days, setting a stratospheric scientific balloon flight duration record. Scientific ballooning operations here on the ice are the result of a unique partnership between the National Science Foundation and the NASA Balloon Program. NASA funds the science, and NSF provides the support to scientific teams and their balloon-borne experiments. Like this one called STO, or the Stratospheric Terahertz Observatory. It's being readied for its first Antarctic summer flight at the NASA NSF Long Duration Balloon Facility at Williams Field. The LDB launch facility is located on the Ross Ice Shelf, a 45-minute drive from McMurdo Station, when the weather's favorable. STO is designed to address a key problem in modern astrophysics, which is understanding the life cycle of star-forming molecular clouds in our Milky Way galaxy.
What we're doing is looking at specific emission features from carbon and nitrogen atoms out in space within our own galaxy.
In doing so, STO will map a swath of our galaxy with the world's most sensitive high-frequency radio receivers, essentially listening in to how clouds of gas and dust, which permeate the Milky Way, coalesce to ultimately spawn stars and planets.
But for instance, no one's actually ever captured a cloud, one of these molecular clouds in the process of formation. No one's been able to see that.
One reason is these atoms and molecules radiate at such a high frequency, over 1,000 billion cycles per second. Too slow to be observed with the human eye, but too fast to be observed through the blanket of water vapor that envelops the Earth's surface. With STO, primary investigator Chris Walker and his multinational team have developed a way to capture and focus this far infrared light using a conventional optical telescope on a high-altitude balloon platform that flies far above most of the Earth's obscuring water vapor.
The light comes in, hits this mirror, goes up to a secondary mirror, and then sends it back through a hole in the bottom of the telescope. It comes right out the bottom of that telescope.
From there, a secondary optic system channels the far infrared light to superconducting detectors held within 5 Kelvin of absolute zero inside a liquid helium-cooled dewar. The telescope and the dewar, Walker is proud to point out, are recycled components.
And the original telescope was built, the way I understand the history, for flying on the space shuttle, but it never flew. And so it was actually in a warehouse at the Smithsonian, I was told.
And the cryostat was a prototype to cool instruments for the Spitzer Space Telescope.
We put the two together and we really have a space-grade instrument that we're flying on the balloon.
Walker is equally savvy about how the economics of scientific ballooning can help further his team's science.
Oh, it's a huge significant stride forward. The main reason is when you compare balloon flights to space flights, you're limited in the size of your payload and the amount of power it can take. You're usually limited to an instrument that weighs a couple hundred pounds and takes a couple hundred watts. But with the balloon, you can actually fly much larger instruments that can look at a whole bunch of more of the Milky Way or extragalactic space than you would normally. In the end, you can do more science than you could from orbit at a much smaller price.
STO was successfully readied and launched on January 15, 2012. Carried aloft by a conventional 39 million cubic foot zero pressure balloon, the STO flight lasted for 14 days, completely circumnavigating Antarctica. The mission allowed extensive testing of many flight systems to be conducted. STO was successfully terminated, recovered, and reconfigured to fly again in Antarctica on December 9, 2016. The STO-2 flight lasted for 20 days, circumnavigating the continent twice. The mission verified the operational capability of advanced flight systems critical to the next generation of terahertz balloon-borne observatories, GUSTO. GUSTO will map the interstellar medium between 4 and 8 times faster than STO-2 and do so for 5 times longer, allowing a significant fraction of the Milky Way and all of the Large Magellanic Cloud to be surveyed in a single flight. It's an example of a new class of sophisticated science payload designed to take advantage of the revolutionary capabilities of NASA's new super pressure balloon platform, designed and engineered to keep science payloads aloft for 100+ days.
So the cutting edge of science is independent of the tool you're using to advance the science. There are still compelling science questions which can be answered on balloon platforms, and since balloon platforms are the most cost-effective way of going after these really important science questions, that's the way we should do it.
What the new scientific ballooning capabilities are offering us is a technology. It's an enabling technology to get us to the edge of space, scientifically meaningful, for a longer duration at a reasonable cost. That's the technology. The need is there's lots of great science to be done that we can do on these platforms at lower cost and get the important training to be able to test out instruments. You know, we may test out things that are very high value on a scientific balloon in anticipation of a future flight opportunity. And so now we've met a need with the technology, and that's real innovation. You know, that's when NASA makes progress.